All right, let's go ahead and get started. My name is Praveen Rokaya. I'm the science coordinator of the core modeling and forecasting team. It is my pleasure to welcome Dr. Nandita Basu today, who is going to present a webinar on water quality challenges and opportunities from the local to the global scale. Dr. Basu is an associate professor and the university research chair of ecohydrology and water sustainability at the University of Waterloo in Canada. She is also the editor-in-chief of the Journal of Hydrology and a member of Royal Society of Canada College of New Scholars. Dr. Basu is a watershed hydrologist and biogeochemist, and her research interest covers a broad range of issues related to water in human-impacted environments, from problems of nitrate pollution in intensively farmed regions in North America to drought in water-stressed areas of India, to urban water pollution and water quality impacts of wildfires. Nandita uses tools from environmental science and engineering to improve our ability to sustainably manage water resources. I believe she will be highlighting some of these work today. Without taking much time, I want to kick off this webinar by thanking Dr. Basu for accepting our invitation to present in this webinar series. The webinar today would be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Dr. Basu, the floor is yours.
Thank you so much, Praveen, and thank you all for attending the webinar. It's been a year and a half into the pandemic, and I still can't get used to talking to a blank screen. So looking forward to engaging with you after the talk. I'm going to talk to you about some of our work today related to water quality challenges across various scales. And before I jump into what our work is, wanted to start by thanking all the people that did the work. So these are students, postdoc from now and before. The work would not be possible without funding from groups like the Global Water Futures, the Canada First Research Excellence Funds, and work done by the tremendous student postdocs. A lot of the water challenges that gain most focus on, with most attention, is water quantity challenges, lack of adequate amount of water, water scarcity issues. This is a really nice report that was done, which brought about this, the fact that water quality challenges doesn't garner as much attention in the water world. However, if you think about the Sustainable Development Goals as an example, water quality is not only one of the six Sustainable Development Goal. Water quality is also intricately related to the other sustainable development goals. For example, if you want to reduce hunger, you have to grow more food. And if you want to grow more food, you add more fertilizers that pollute the water quality. So there's a tight linkage between water quality and the different sustainable development goals, which is one of the reasons water quality challenge is often referred to as a wicked problem. That is, you try solving it and something else pops up, and it's really important to think about it in a holistic way. If you think about water quality, well, there's tremendous progress that we've made in terms of dealing with water quality. In the 1900s in US, there was a significant fraction that were dying from diarrhea, and now that is really much less. However, water-related diseases are the leading cause of death in the world, killing about 1.4 million children per year. Over 80% of the wastewater is discharged back into rivers, streams, lakes, and oceans. So even though bacterial problem is not so much a concern in the developed world today, in the developing world, it is still a big challenge. In the developed world, we still have bacterial contamination issues. This is drinking water advisories by the First Nations community. And here you see that there is 67 long-term drinking water advisories that have not been fixed. And this is Canada. Across US, you see the same thing. Approximately 1 in 10 Indigenous Americans lack access to safe tap water or basic sanitation. Another water quality problem really plagues us today, and that is algae, so eutrophication and algal blooms that is caused by excess nitrogen and phosphorus running off from our agricultural fields or from our urban lawns and polluting our waterways. We have eutrophication, which sucks the water out of oxygen, and we also have incidences of blue-green algal blooms that produce toxins that severely threatened our drinking water treatment facilities. On the right, you see an image of a glass of water. So that was how the water intake at the Toledo water treatment plant looked like a few years ago when the plant had to be shut down because of a massive bloom in that region. Water quality is just not only a surface water problem, it's also a groundwater problem. Indeed, nitrate in groundwater is one of the biggest challenges. This article that came out in New York Times talked about the fact that that nitrate in drinking water was really significant, and it was really impacting human health. A lot of our work focuses on this part of the story, thinking about water quality problems, diagnosing them, and modeling water quality problems. In the last few years or so, I've also gotten more interested in thinking about solutions to these problems. There's only so long you can imagine thinking about problems. And in this case, one of the things that our group really is interested in is thinking about water quality solutions that also address other sustainable goals. So synergies amongst various solutions is important to think about. So I wanted to start off talking about some of our unpublished work in the world of diagnosing of water quality problems. So here we are looking at a data set of about 170 to 200 water quality stations across the Great Lakes Drainage Basin. And of course, you see there's much more stations in the Lake Erie and the Lake Ontario drainage basins. What we did in this case is we took water quality data, we cleaned up the data in different kinds of ways, and we developed a machine learning model, a random forest model for dissolved inorganic nitrogen, soluble reactive phosphorus, particulate phosphorus, as well as nutrient ratio. So soluble reactive phosphorus to total phosphorus and the nitrogen to phosphorus ratio. The benefit of these kinds of models is they really allow us, these data-driven models really allow us to understand what is going on in the system, what are the primary drivers, and then this helps us to build more sophisticated process-based models once we have a better idea. So in this case, we developed these partial dependence plots that showed us that soluble reactive phosphorus concentrations increased with increasing percent developed land or agricultural land, as well as tile-drained land. So to increase in tile drainage, in this case, is shown to increase the soluble reactive phosphorus. Concentrations also decreased with increasing wetland area, showing that wetlands are a good strategy. Dissolved inorganic nitrogen followed a similar trajectories where concentrations increased with increase in tile drain and decreased with decrease in the wetland area. None of this is really surprising. We know that when there's more ag, there's more of nitrogen and phosphorus that's coming out. What was really interesting and somewhat unexpected is this relationship where we found that the bioavailable phosphorus fraction, so the fraction of the phosphorus that's in as soluble phosphorus, increases with increasing livestock density. And the reason this is important is because the SRP, the bioavailable phosphorus, is what drives a lot of algal blooms because it's in a form that is most easily accessible to the biota. And what we are seeing here is that increasing livestock density is increasing that ratio. We've been thinking about why this is so, and one of the hypotheses is that in areas where livestock density is high, you've been adding manure, you've been disposing of the manure, so you've been adding manure to these landscapes. over many years, and that has really built up the soil test phosphorus in these soils. And when you have high soil test phosphorus, when you have tile drains and high soil test phosphorus, the water flows through the system and leaches it out in a soluble form, and that goes into your streams and receiving water bodies. So that is possibly a reason for higher bioavailable phosphorus fraction when you have high livestock density in a particular watershed. Now, there's two things that I want you to take away from here. The first idea is this basic idea that these build-up and legacies in the system, which you will see me talking about. And then the other idea is the idea of importance of manure in the system and need to address the issues related to manure. So bringing you back to this idea of nutrient legacies, the idea of legacies is that we have been doing agriculture in our landscapes for many decades now. And because of that, we have these pools of nitrogen and phosphorus that have built up in the landscape. Because of these pools, when you make a change now, it takes time for water quality to improve. Here's an example of an article now dated now from 2017, which said that a 5-year fight removes less than 1% of the phosphorus from Lake Winnipeg Basin, despite having spent $18 million. Such lack of success generates skepticism. One of the reasons why you see this lack of success is because of these legacy stores of pollutants that has built up over decades of agricultural intensification. So when you want to improve water quality, you really need to think about these legacies and really factor them out in your strategies. So our hypothesis that a lot of our work focuses on is that intensively managed catchments have legacy stores of nutrients that have built up over decades of fertilizer application. And these legacy stores contribute to catchment time lags. So for example, if you stop fertilizer application today, what legacy means is that it will take 10 years, 15 years, 20 years for your water quality to get better. And you need to consider that into your management strategies. The questions that you want to think about when you think about legacies come in these two boxes. One, which is how much legacy is there and where is it and what form is it? So when you're thinking about nitrogen, for example, you can have legacy that's dissolved in your groundwater. We call it hydrologic legacy. You can also have soil organic nitrogen buildup in your root zone of soils. We call it biogeochemical legacy. When you think about phosphorus, you can see a lot of legacy that can build up in reservoirs, in stream sediments, and this is what we also call as network legacy. So whenever you have one watershed and you're trying to design management for that watershed, you need to understand where the forms of legacy can exist. And then the second question, well, there's these pools, how are they mobilized? Because if they were just pools that were not mobilized, I wouldn't care because they would not impact my downstream waters. So it is important to understand how these legacies are mobilized. And in this case, a changing climate is really, really important because when you have increasing intensity of precipitation, you mobilize these legacies faster, and this leads to down gradient water quality pollution. So some of our work has focused on quantifying these legacy masses. So here's an example of work I did when we were in the US, and we looked at legacy nitrogen. And here we found evidence of organic nitrogen accumulating in the root zone of agricultural soils. And it was a significant amount that was accumulating. So as an example, when you do agriculture, you're typically adding 150 kilogram per hectare of nitrogen. Legacy accumulation magnitude can be as much as 50 kilograms per hectare. So if you stop that 150 kilograms per hectare, that 50 kilograms still would have to be used up before you see a water quality improvement. Legacies not only accumulate in agricultural soils, they also accumulate in cities. So this is a really interesting study that what they did was they looked at soil data in cities and they compared it to soil data in nearby natural regions. And what they found is that the soil data in urban areas, which is the red dots, is significantly greater than the soil depths in nearby urban areas. And the difference is, of course, greater when you go below a certain depth, and this is parallel to our agricultural finding. They also found that smaller cities accumulate more soil organic carbon. And if you think about smaller cities, they have more urban lawns. And in lawns, you're putting in a huge amount of fertilizers, and there's not much nitrogen that's leaving the system via crop harvest. So there's a buildup that you see in these systems. There's another study that looked at nitrate storage in the vadose zone, and they found that nitrogen has been increasing in global aquifers all across the world. So why does legacy matter? So here's an example with some data across the world, which shows that if you look at like a snapshot in time, so this is average over 10 years. So if you look at snapshot in time, you see that nitrogen input, so this is fertilizer, manure, atmospheric deposition, and nitrogen loads, which is what's coming out, have an approximately a linear relationship. So this is work that was done by Danica Bryans in our lab. However, now if you go into the time domain, so take any one of the watersheds over here and expand it in time, what you see is this beautiful hysteresis behavior. So what this is telling you is if you start in the 1970s, which is the dark green diamond, and as you increase the nitrogen inputs, your nitrogen load is increasing. All well and good. And then after 32, you say, well, I'm going to decrease the nitrogen input now, where the nitrogen load are not increasing. Nitrogen load instead of decreasing, they keep increasing. And this is this idea of legacies in the landscape. So there is stores of nitrogen in the landscape that's bleeding out. And you see this anti-clockwise hysteresis pattern, where for the same nitrogen input, you're getting a much higher nitrogen load in the system. Here's another example from a river in Denmark where this kind of behavior was not apparent, right? So in this case, there was a more linear response. What we are trying to do is really look at data across many, many watersheds across the world to understand what drives these hysteresis loops, and can we predict it for ungauged basins. Now, all of these are data-driven work. The next stage is also to think about models. How can we explicitly incorporate legacies in various water quality models? I'm not going to bore you a lot with model details, but one of the things to keep in mind is when we started doing this work, we first asked the question, why do we want to build another model? Because there is a gazillion water quality models out there. And one of the things we realized when we were looking at the available water quality models is to incorporate these long legacy buildup in these models, it was really hard. So we have one paper where we tried building it up in SWOT, and it is possible, but it is really hard. And the reason is we are talking about simulating for the last 50 to 60 years at the least. Land use is dynamic, so your hydrologic response units are changing. So you have to build up these legacies in these various units, and then we have to say how that impacts water quality. So as an example, if you think about it, let's say a particular block of land is under corn right now. In a regular model, you would say, well, if it's corn, this is the amount of nitrogen it's going to leak out. In element model, it's also important to say, well, what was the past land use? And the past land use would also impact its current water quality. Apart from that, the element model, which is what our group works on, is a process-based model that uses carbon-nitrogen cycling in the source zone, which is what is the root zone of agricultural soils. And then we describe groundwater processes using a unique travel time-based approach to predict nitrogen loading at the catchment outlet. Again, if anybody wants to know more, I can talk more about the model. We use this model for the first time to predict nitrogen loads in the Gulf of Mexico, where nitrogen is a big problem. And what we found over there is if you're talking about nitrogen concentrations at the outlet of the Mississippi River Basin, it will take 35 years to achieve the 60% reduction goals that have been set up by the Gulf of Mexico Hypoxia Task Force. Now, the caveat to that statement is that this is assuming that you're doing only farm scale nutrient management. So you're reducing fertilizer application rate or adding cover crops. It does not take into account that you can still do more downstream controls like reservoirs or wetlands or riparian buffers that would make the process faster. Okay, so now, coming from all over the world back to some of our Canadian watersheds. So in this work, we have developed an element model for 14 sub-watersheds of the Grand River watershed. So in the purple, you see watersheds along the main stem of the Grand, and then you have the various sub-basins within the watersheds. And we developed element model for each of these basins. Overall, the model did really well in terms of our predictive ability. And again, note the x-axis in here, we are trying to model the response from the 1940s to current. The thing that element model does, which other models cannot, is it can then tell you how much legacy is accumulating in the various pools. So in this case, if you look at the left-hand image, this is one watershed. So this is the entire basin. The black line is the nitrogen surplus. So this is the difference between the nitrogen inputs as fertilizers, as manure, as atmospheric deposition, and nitrogen output as crop harvest. So you see, that's the black line. And then the different pieces, the red part is how much soil organic nitrogen accumulation you have. The blue is groundwater accumulation. The yellow is the denitrification in the landscape. So this includes both the denitrification in the soil as well as the groundwater and streams. Purple is the wastewater treatment plant removal. And the gray is what's going to the stream. So now this is the entire basin. Now, if you break that up, so each of these rows in the figure on the right is a specific sub-watershed. And you see that there's a lot of spatial variability. So some watersheds like this top one over here, this is the Kanikajee watershed, which is a very, very tile drained watershed. And here, here you see that the stream load is a significant portion of the nitrogen load in that watershed. Whereas in the Grand, you see a lot more of soil organic nitrogen accumulation. So these factors vary across the basin. And then we ask the question, well, what controls this legacy accumulation? And the thing that we found that was most interesting is that the tile drained area, the percent of the land that was tile drained, was by far the most important control on the amount of legacy accumulated. And this is really interesting because this is talking to the fact that we have modified these landscapes so much that any natural feature of the landscape is completely overshadowed by the presence of these drainage pathways. So for those of you who are not familiar with tile drains, these are perforated pipes that are, if you look at the image on here, that are put in the soil about 1 meter or so depth to allow the corn roots to grow so that the land is drier and your crops can have a good crop yield. And what we find is that as you increase the tile drain density, you are impacting both the soil organic nitrogen accumulation as well as groundwater organic nitrogen accumulation. Using these relationships we developed for some of the small sub-watersheds within the Grand, we then scaled it up to the entire basin. And you can get these accumulation maps for soil organic nitrogen and groundwater. And when we ran future simulations with the model, the biggest thing that came out is that how fast your water quality impact is very strongly related to the amount of legacy that has accumulated. This work is now being expanded to do the Lake Erie Basin to really understand the magnitude of accumulation in the basin, as well as the timescales of recovery. Another piece of work that's going on focuses on taking actual measurements of groundwater nitrogen and seeing if we can validate some of these estimates. Work is also being done in this space in the Chesapeake Bay Basin. This is a recently accepted paper by Shui Chang and Kim Van Meter. And here they are again exploring the question about lag times and legacies in various sub-watersheds in the Chesapeake Bay Basin. Okay. So now I'm going to jump solute from nitrogen to phosphorus. We also developed element model for phosphorus, and in this case, you see in the soil we have organic phosphorus and mineral phosphorus. Within organic phosphorus, you have the active and protective pool. The phosphorus model that you see for our source zone is very similar to what goes on in a model like HYPE. So we took the source zone part of it and we added it to our model. Of course, when you're thinking about phosphorus, erosion is a big part of the story, as well as retention in reservoirs and riparian areas. And there is also the groundwater travel time distribution. The other big piece of the phosphorus story, which takes some time to figure out, is the wastewater component and how wastewater treatment plant efficiencies have changed. So there was a lot to do to figure that out. Here, this is an example of how we went about it. We have dish detergents, we have laundry detergents, we have food. Some of the household stuff gets through the septic systems, gets into the landfill. There's food that is wasted. Wastewater treatment plants have their efficiencies, so there's some removal from them, and the biosolids go to croplands, or they can go to surface water, and some of the biosolids can also go to landfill. So we figured all those out with coefficients that was present from various reports around the Grand River Basin. Lots of details that's hidden in here with phosphorus that is not necessary for nitrogen. Using all this, we created for phosphorus, the phosphorus budget. And what you see that's really interesting over here is that though human waste, which is the purple, has increased since the 1970s, the yellow highlighted line, which is the domestic phosphorus loading to the river, has actually decreased a lot. And that is because of our excellent wastewater treatment plant facilities, as well as detergent phosphorus bans that have helped that. Now, if you put that together, of course, into an overall watershed phosphorus budget, which you see on the right here, the purple, which is your domestic phosphorus, is really a small piece of the puzzle. And this is important to remember, because when you think about upgrading wastewater treatment plant to solve the phosphorus problem, you won't be able to solve it because it's a teeny tiny part of the budget, unless you're working with a very small urban watershed. Here's the phosphorus inputs and outputs. As you see, a big part of the budget is manure phosphorus. So again, we really have to address the manure problem. And then there is fertilizer phosphorus. The other thing that's important to note here is that phosphorus surplus has been decreasing since the 1970s. And this is because crop uptake has become more efficient. So we use all that in element model, and in this case, we have not done the sub-watershed modeling yet. So we modeled only the outlet of the Grand, and overall our model did a decent job of predicting the annual phosphorus loads. The benefit of models like this is it allows us to understand where the phosphorus is hiding to be able to target it. In this case, we found that a lot of the phosphorus is there in the soil. So just to give you some idea of numbers, our model results suggests that since 1900, only 4% of the net phosphorus inputs have been exported to downstream rivers. 96% is still left as legacy P in the watershed. So when we think about water quality problems and how to address it, it is important to remember that there is this 96% that's left lurking there. models are only as good as the data available. One of the biggest challenges with water quality models, or with any model for that matter, is that we are calibrating it with only one time series of water quality data at the watershed outlet. And the model has hundreds of parameters that we calibrate to. So there's huge issues of equifinality. In this work, what we tried doing is asking the question, can we find other sets of internal data to validate that model? Remember, I told you that there is phosphorus built up in the reservoirs. So in this case, we took sediment cores in the reservoirs in collaboration with Professor Ronald Hald in biology. And we asked the question, can we independently validate reservoir phosphorus accumulation? And we found that indeed we can. We took the soil core, we did lead 210 dating of the sediment core, and we were able to relate the phosphorus accumulated within the sediment core with our modeled estimates. And we found that they were really close, which allowed us to increase our confidence in the model. And then, of course, once you have a model, of course, we are trying to predict the future. We did multiple scenarios. And in essence, what we found was that the biggest impact we get was manure handling losses. So if we address the manure issue, we were able to get much faster a reduction. If you were trying to address the legacy phosphorus issue in the soil, that took a much longer timescales for water quality improvement. What are we doing with this now? This is work done by a PhD student in Lake Futures, Lamesa, and she is looking at multiple watersheds within the Lake Erie Basin and looking at inputs and outputs of phosphorus. And then we are developing also element models for various sub-watersheds within the Lake Erie Basin. This is also partially funded by Environment Climate Change Canada and the Global Water Futures. Okay. So the last 15 minutes that I have, I want to switch gears from modeling of water quality problems to thinking about solutions to water quality problems. And I'm going to talk to you about 3 groups of solutions, 2 in which we are actively working on, and another one where there is a huge potential to make a difference. So the first one is legacy as a resource. If I keep talking about the fact that nitrogen and phosphorus is building up in our soils, can we effectively harvest it? And the short answer to that is yes. This is a paper that came out in Global Change Biology, where they found that less than half of the nitrogen taken up by crops is derived from the current year fertilizer. So the crops are already taking up the nitrogen from the past. If we stop putting so much in, we might be able to make a difference. And in fact, the study that was done by a big group here in Ontario showed that this was indeed the case, where there was this groundwater well where nitrogen concentrations were increasing. This is work by Dave Rudolph and others. Somehow the name got cut off. Where there was this well where nitrogen concentrations were increasing, and the city of Woodstock decided that they, instead of building a water treatment plant, which most people do, they would invest in watershed management. So they took a region around the wells and paid the farmers to do really stringent nutrient management. So apply little fertilizer. So fertilizer applications were reduced by 50%, livestock operations were managed, and they found that nitrate concentrations decreased in the soil water, but crop yields did not change. Again, proving that a lot of times we can sustain the fertilizers that we have put in for the past 3 or 4 years and improve water quality while not sacrificing on crop productivity. This really interesting review paper that came out in Environmental Science and Technology suggests the same thing. They talk about the fact that a lot of times all we measure in the soil is soil test phosphorus, which is only a small piece of the puzzle, as you see over here. It's only 15%, but there's this large amount of legacy phosphorus that's available. It's not slowly available. It is mostly available. And if you reduced phosphorus fertilizer application rate, you would be able to tap into some of these legacy phosphorus sources. And indeed, a study done by Jian Liu and Helen Balch and others showed that a 60% reduction in fertilizer P application can lead to a 40 to 50% reduction in total dissolved phosphorus over a 10-year period with no reduction in crop yield, right? So it is possible to address the problem without sacrificing on crop production. How do we go about doing it? Well, so the other part of the story before I go into that is this can have both water quality and climate benefits. So in this case, if you're reducing fertilizer application, for example, you will reduce not only nitrate concentrations in the streams, but you can also potentially reduce N2O emissions and thus address climate mitigation target. There's a recent paper that also came out that quantified how much methane was emitted by eutrophic water bodies, and it was significant. So again, if you solve the water quality problem, you can also address the climate problem. So again, water quality challenges that address multiple sustainable development goals. Now, what is it that is needed to do this? What is needed is, one, a lot of understanding on where this legacy phosphorus or nitrogen is to be able to tap into it. So a lot of strategic data collection, emerging technologies, so remote sensing and other technologies that can figure out soil carbon levels, soil nitrogen levels to really tap into this. And most important probably is a different policy and incentive structure that makes it happen, so that when farmers are applying maybe less fertilizer and somehow the crops are not that good, there's insurance structures in place to protect against such losses. So the solution is tied up in these policy changes. Okay, so jumping gears on yet another problem and yet another solution. If you remember, I was talking to you about manure. Manure as one of the biggest components of the phosphorus inputs in many of our watersheds. This is true about Ontario. This is also true about the prairie landscape. Manure is a big part of the puzzle. And this is not only specific to Canada, all over the world. There's a huge amount of manure that is being produced and it impacts our water quality. The problem with manure is the intensification of agriculture. So once upon a time, our agricultural landscapes looks like this. You had few cows grazing in the fields. You had cow poop that was automatically fertilizer for the soils. Now, agricultural operations look like this. So you're generating a huge amount of concentrated manure. Manure is not the easiest to transport across large distances. So at the end of it, they are dumped in excess of the crop fertilizer needs and lead to water quality problems as well as greenhouse gas emissions. There is this US scale study that was done that showed that as you increase percent of manure N, so if you think about total inputs and how much proportion of that is manure, as you're increasing that, your nitrogen use efficiency is decreasing. And the nitrogen use efficiency is basically how much nitrogen you're getting out as crop versus how much nitrogen you're putting into the soil. The reason this is really important is because ideally, you would want this efficiency to be close to 100% or 80% so that most of the nitrogen you're adding to the soil is taken up by the crops and you don't have excess to pollute your waters. And here you see as manure is increasing, that efficiency is decreasing. So how do we solve this problem? Well, one of the solutions is use of the manure as biogas. And there's work that has been done in this context. And it has been shown that manure does have a huge potential in terms of providing for biogas and providing an alternate energy source, and both providing jobs as well as an alternate energy source, as well as improving water quality. However, despite the knowledge that exists about the value of manure as an energy source, currently there is not significant adoption of biogas plants around. We did this one study across US where we asked the question, what is the feasibility of biogas operation at a regional scale? What would it take, and what potential does it have in reducing the manure problem? I'm not going to go into the details of this approach. This is really preliminary, but what it suggested is that this is completely an economically feasible possibility. Right now, of course, manure reuse in biogas is done more on a case-by-case basis and not in a coordinated way. This work is going to be continued in a recently funded project where we will be exploring this manure to biogas question and developing spatial optimization models for siting biogas plants, both in Ontario as well as in some of the prairie provinces. Okay, I'm going to jump into the third and last solution scape that I wanted to discuss, which is wetlands. So if you think about the first two that I discussed, they address the source of the pollution. So the manure is the source of the pollution, the excess fertilizer is the source of the pollution. But some of the pollutant has already left the system. It might be in the groundwater, it might be in my reservoir. How do we deal with that? And that's where wetlands come in. Again, in the world of wetlands, it's not that we don't know about wetlands. We've been restoring wetlands for many decades. We know that wetlands retain excess nutrients and improve water quality. What our group has been working on is addressing this question at the landscape scale. Asking the question, how do wet landscapes look? How have humans altered these landscapes? And how has these alterations impacted their ecosystem services? And can we do better? So when you're trying to restore wetlands, you ask the question, which wetlands should we restore? And how many do we need to solve our water quality problem? So to answer this question, we started talking about this 2 years ago at 2019 AGU. And this is interesting. I'm looking forward to 2021 American Geophysical Union meeting because sometimes the most fun science happens at these coffee shops. So here we ask the question, how much nitrogen is removed by wetlands across the continental US? Really simple question. To answer this question, we first looked at spatial data on National Wetlands Inventory data. So here we looked at data for 30 million wetlands across the country. We had done previous work where we estimated nitrogen removal by wetland as a function of wetland size and wetland nitrogen input. So we put all that together. And we developed this map of percent nitrogen removal by wetlands across the country. And here you see the patterns are similar to wetland density. So in areas that you have dark purple colors, those are the areas where you have high density of wetlands. And so that's where you have more wetlands, you have more potential of removal. But here is where the catch comes. Is there nitrogen sources in those areas? So here we are linking nitrogen sinks with sources. And for nitrogen sources, we do a lot of work thinking about sources of nitrogen in the landscape. And here we did synthesis of 90 years of agricultural data to come up with nitrogen inputs to the landscape. And that's the input map. And here you see the input map is, of course, greatly concentrated in the Mississippi River Basin, in areas in California. And using this input map and the percent removal map, you can then estimate how much nitrogen is being removed. And we ended up with a number of 0.86 teragram of nitrogen across the country. What does that mean? It means that without existing wetlands, nitrogen loads in the Mississippi River Basin would be 50% higher than they are now. And that number is important because while we all knew that wetlands are important for water quality, it's important to realize that if we double the nitrogen load to the Mississippi River Basin, what kind of economic damage it can cause. And the fact that loss of wetlands can lead to this much impact. The other thing that was really interesting, what we found is that the nitrogen sources are decoupled from wetland locations. So what we see over here is on the x-axis is wetland density and on the y-axis is nitrogen input. And you see the red areas where you have low density of wetlands, but high amount of nitrogen surplus. Whereas the yellow areas where there's a ton of wetlands, but there's no nitrogen in there. So this is giving you the first guide as to where you should place the wetlands for best water quality improvement, where you should protect the wetlands. And so here we are answering the question, how can wetland restoration lead to improvements in water quality? And I'm not going to go into the methodology of how we did that, but we did different modes of wetland restoration. So here we said we are going to increase 10% in wetland area across the country. And this is random placement of wetland restoration. The reason this is probably one of the most important strategies is because that's how wetland restoration happens today. It's completely random across the landscape. And here, and this is the second, which is similar 10% increase in area, but no agricultural land loss. And the third, which is the targeted restoration. Here we are actually optimizing the placement of wetlands in locations where the nitrogen inputs are high. So you get more wetland densities in the Mississippi Basin. Now, what we find is really interesting. In this case, let's say we are talking about 10% increase in wetland area. If you have the random, you'll get, if you get the no agricultural land loss, really little benefit. If you take the random placement, you get some benefit. But if you do the targeted placement, you get 40 times more nitrogen removal for the targeted placement compared to the random placement. And now if you do cost, so same plot, but now the y-axis is cost, it's still more, but only twice the cost of non-targeted restoration. So it's important to remember that you're getting 40 times the benefit at twice the cost. So to summarize, here we found that a targeted 22% increase in wetland area in the Mississippi River Basin could result in an approximately 40% decrease in nitrogen loads, bringing us closer to the policy goals. Of course, important again to remember that wetlands also sequester carbon and provide multiple other ecosystem services, so they address multiple sustainable development goals. Current work, we are expanding this from nitrogen to phosphorus, and in a project funded by Ducks Canada, we are going to expand this work to the Lake Erie Basin, and specifically again ask the question, how much are current wetlands in the Lake Erie Basin, how much phosphorus are they removing, and what is the potential for wetland restoration? The phosphorus question is a little bit more challenging and a little bit more fun than the nitrogen questions, because wetlands can be both a sink of phosphorus, but they also can be source of dissolved phosphorus in certain seasons. So we really need to take that into account. So to summarize, the few key takeaways: water quality problems are wicked problems, and legacies impact water quality, but also current practices impact water quality in ways that we don't always understand. Technological solutions exist, but sometimes we need change in regulatory and policy framework, as well as a proper incentive structure that will facilitate widespread adoption. And we need to think about these synergies to kind of tap into the policy framework. So water quality solutions that also address climate change, that also address biodiversity solutions, is really important to consider. And there is no silver bullet. Need to think about solution portfolios. So in this example, I talked to you about 3 separate solutions. A real life solution portfolio will include all these solutions to accelerate water quality improvement. With that, thank you for your time. And if you have questions, feel free to email me or send me a Twitter message.
Thank you, Nandita. That was a very fantastic talk. We'll be now moving to the question and answer session. We have a question from Amir.
Do you want me to stop sharing or keep sharing?
Anything is fine.
Okay.
If you want to see the screen, then if you stop sharing, then that will.
Okay, I'll stop sharing, and if there's any specific figures related to it, I'll.
Sure.
Okay.
So the question from Amir is, would increasing application of fertilizer but preserving wetlands or even constructing artificial wetlands be a better balance between the feeding the people and improving the water quality?
I would say no. Is a simple answer, right? Because the challenge is so big that we actually need to do both, and depending on where you are is also part of the answer. So if the question is about North America, we are already applying a ton of fertilizer, and some of our work shows that you can actually get similar crop yields with less fertilizer application. So you don't need to apply more fertilizer. But if you're talking of the developing world, there's portions of the developing world that less fertilizer is being used. I would say we should be very careful in those places as we are increasing fertilizer use to see if you really need it and to really optimize for it. Because in some ways, the way I'd like to think about the fertilizer versus wetland is like if you're sick, right? If you're running a temperature, you take Advil to get your temperature down. That's your wetland. But you still have to take care of your underlying problem in order to get better in the long run, right? So you have to do both.
Thanks. Next question is from Jane. Do you think the tile drainage effects is directly due to the drainage tile, or does it reflect higher yields and agriculture intensity on the drained lands?
Thank you. That's a really good question. The challenge with that question is that it's so difficult to decouple those effects. So it is a function of all those effects. When we did our machine learning, we did these things called partial dependence plots, where what we do is in a really simplified way, where what we do in those relationship is we hold one variable constant. So we tried doing it a little bit by saying, let's take agricultural land constant and see what is the incremental effect in that model on tile drain, right? And so in that case, we saw even when you hold agricultural land constant, incremental effect of tile drain is increasing some of the concentration. So that's the only way that I know how to decouple that effect, because they are so correlated with each other, you can't otherwise.
Thanks. It's not a question, just a curiosity. You have also worked in India and in a lot of places like in developing countries. A lot of time the focus of the policymaker is set term, like 3 to 4 years when they have the mandate. But some of these that you saw that it can take up to decades to get some answers, some solutions out of that. So I think it's very hard to convince the policymaker in that situation. So have you thought about it, or like just wondering about it?
So the good question. I mean, and that's not just a developing world question. That is North America question too. That one of the big challenges to addressing this is the time scale of policy and decision making, which is more like 3, 4, 5 years, right? And so when I started talking about legacies, people would tell me, don't talk about it. Nobody will do anything if they know it won't have an effect. The flip side of that, and I've seen that in some places that I've worked in, is so this is both stories from places in the US that I've worked in, as well as stories from people in Europe that have done similar work, is when you tell people, you don't tell people about legacies, you tell them, okay, you do this and water quality will improve, and then it doesn't improve after 5, 6 years, you lose trust. Right? Because they come back and tell you, we did whatever you told us to do, but nothing happened. So I think we have to write that fine balance. And the biggest thing to do is to educate the policymakers that it is a long time scale. And so what you're putting on the landscape today is going to be there for a long time, and you need to think about that. I mean, climate change is a similar issue because it's not something that's going to be solved tomorrow, but still we have to work towards it.
Also on the use of manure, you also talk about using it as biofuel. And I remember back in days, like when I used to go some of the southern part of Nepal, and then in some indigenous communities, they used to use cow dung. They used to mix it with the hay and then use it as like fuel to cook food and stuff like that. So do you think that could be another potential solution?
So sometimes, I'm moving towards a collaboration with groups in India. So broadly, yes, I think bio energy is one of the solutions to water quality challenges in the developing world, whether it be kind of more old world ways of doing it, which is what you and I grew up seeing happen, or whether it be more sophisticated ways, like an apartment complex, instead of disposing of its waste to a local lake, now has a biogas manufacturing on site that they use for their electricity, right? The thing to remember is sometimes some of the old world ways also generate a lot of air pollution. So it's important that, so I wouldn't say that we should go back to that. I think we should use the essence of that. But I think use of waste, because, you know, in the developed world, we talk about manure, but in the developing world, it's not only manure, it's human waste that is a big water quality challenge. So ways of addressing it, because you can't afford wastewater treatment plants. So ways of addressing it is really important.
So when I think about water quality modeling, sometimes I feel like, you know, you have this meteorology group that works in, you know, like climate data, and then you have hydrology group that uses climate data to generate flows, and then water quality will use that flows to do water quality. So there's like natural cascade of uncertainty from, you know, different, from, you know, like climate data to hydrological models, and then hydrological model to water quality models. So like, have you done anything to address this cascade of uncertainty, or what is your approach to deal with the model uncertainty in your simulations?
So we do. So there's a recent paper that's going to come out probably soon with a group in Germany, where we are explicitly tackling a lot of these uncertainties in a broad kind of way. One of the things, I mean, whenever I have students, postdocs coming in who've been trained primarily in hydrology, I have to spend some time saying, getting 2 data points a month is okay. Because when you come from the hydrology world, it's like, oh, I'm going to throw that out. But the water quality is a really different world in terms of the bounds of uncertainty in the data. The good thing is a lot of the water quality trends are driven by flow. So I say a lot of times, if you get the flow right, you are halfway there. So a lot of what we do is kind of zone in on that water quality piece, knowing there's significant uncertainty in there, but then also knowing that there will always be that uncertainty, and you would have to make predictions and management decisions within that space, while there's also a huge amount of space for innovations in other monitoring techniques.
Thanks. I don't see any more question in Q&A button. I'll just give a few seconds for anyone if they have any last questions to ask before we formally close this webinar. So,
and if anybody's interested, just a plug, anybody's interested in any of this work, please feel free to reach out. Don't have any specific projects openings now, but there's ongoing opportunities within the group to be able to work.
So I don't see any questions, and we're about 3 minutes to the closing. So I think we'll move towards the formal closing of this webinar. Thank you again, Nandita. I also want to thank everyone that attended this webinar. The video recording will be available later today in Core Modeling website. Just a note that next week we'll be having Dr. Maria Helen Ramos from French National Research Institute for Agriculture, Food and Environment, who will be presenting on the quality and value of the hydrological forecast and prediction. So please stay tuned. That will be all for today, and thank you again, and please stay safe. Wish you a good day. Any last comments do you have, Nandita?
No, thank you again for inviting, and hopefully we'll see everyone in real time sometime soon.
Thanks. Bye.
Take care.